I'm Fran, and I'm going to try and talk about what a random number is and why we should care about this. So, Stack Overflow, the source of all knowledge buried deep in the comments, is a perfectly picked random number. So, which begs the question, like, is that a random number? Who knows? In fact, although I've titled the talk, What is a Random Number and Why Should You Care? Lesson number 1, even though it was on Stack Overflow, 59 might not have been a random number. In fact, I think we can prove it's not a random number because there's no such thing as a random number. What you can have is a sequence of numbers, or tosses a coin, heads and tails, anything like that. You can have a sequence that appears to be random. Donald Knuth said this, and he's always right. Certainly more right than Stack Overflow. Some Stack Overflow answers are correct. So there's no such thing as a random number. What you might have is a sequence of things, and you can't necessarily predict what's going to happen next. And that's the clincher, is the unpredictability. So if you just got a random event, you can't be sure it's random. There's nothing to predict there. You've just got the number 59 for the last one. So we're talking about sequences of things here. And these sequences that might seem random, if I toss a fair coin often enough, I might expect in the long run to have half heads and half tails. So even though I'm talking about what might be a random event, whatever random means, I can still have properties of random things. I can talk about the mean, the expected outcomes, 50-50 heads and tails for coins. I can talk about how much variance I might expect, and so on. So I can talk about some statistical properties of these. One little aside, that word random doesn't mean quite the same thing as chaotic. Chaotic things are quite hard to predict. We'll do a little aside into what chaos means midway, if I pace through this properly. What we're mainly going to talk about today is what we do when we're doing development work, and that's pseudo-random numbers. So they're not actually random, but we still don't know what random means. So, could you even tell if this sequence, like we've already agreed, we can't have a random number, that's nonsense. We can have a sequence of numbers. If you had a random number as a service or something, and it kept returning 9, is it generating random numbers or not? Maybe. Could you prove something's not random? Well, if you always got 9, you could prove it was always going to give you 9, then maybe it isn't random. You might not be able to tell what's going to happen next. So I think, as I started preparing this talk, I've come to the conclusion, A, there's no such thing as a random number. We have a sequence of things that we can't predict what's going to come up next. But if you toss a coin, and you knew the precise initial conditions and enough physics, and I'm more of a pure mathematician than a physicist, in theory, you ought to be able to work out exactly what you're going to get. So tossing a coin's not random, it's not doing the physics properly. Okay, so there's no such thing as a random number. There might be a sequence of seemingly random events, but we're not really sure what random means next. More importantly, why do we care? Well, several things we care about. A lot of times people get attempts to generate random numbers wrong, attempts to use the random in whichever programming language you picked on wrong. And also, it makes things much more interesting. If you're writing games, you want something surprising or unexpected to happen, otherwise it just won't be any fun, right? And lots of card games involve shuffling the cards, and first-person shooters, something will materialise somewhere different each time, otherwise it would be boring. So, inject a bit of excitement, a bit of interest. And there's some things, like for example, COVID modelling or financial pricing and stuff, that the maths is just way too hard. So we go, hang it, we do a model, and we run it several times over using these pseudo-random numbers, and just take an average to get a feel for what sort of thing might happen. So it can actually be pragmatically useful for a variety of circumstances. And I seem to be on the testing track, so I might talk about testing, but I'm frequently talking about testing. So, to prove why this is interesting, can you code your way out of a paper bag? Some of you can, some of you got certificates.
Yeah.
Hey, well done. I've got a signed certificate as well, so thank you to anyone who signed this years ago. What we need is something representing a paper bag, so just leave this in 2 dimensions, which I haven't up to my game to 3 dimensions and boxes yet. That's around with my cat, hiding in boxes. If we've got some blobs, and they just move up a step at a time, they go out of the bag, right? All proving I can code my way out of a paper bag in a variety of different ways, but we'll just see a couple of things today. Now, what's a random number and why do I care? There's no such thing as a random number. Why do I care? That, even though I have coded my way out of a paper bag, was really quite boring. So over the next half hour or so, we'll bring in some randomness and make it slightly more interesting. That's my plan. Yes, I remembered to do a demo. Well done. How do you generate some random outcomes? Anyone use C here? Python? Some of that C#? C++? Okay. I've not got time to do my C++ now. Remind me later on, there's 3 cards on chairs randomly placed. Or, well, was it random? But I was marking that later on. Each of the programming languages have got slightly different variations on how the random works. And some of them are easier to use than others. C's is really easy to get completely wrong. Even just simulating rolling a dice. Yeah, things go wrong. If you're switching between languages or learning one for the first time, just hold in mind 2 questions. Sometimes, if you call random over and over again, like for example in C, you always get the same starting number and the same sequence of numbers. But sometimes it seeds it for you and you get a different sequence each time. So first question, do I need to seed this or not? If I want different numbers each time. And then the next question is, if I wanted to simulate rolling a dice, for C#, we do random next 1 to 7, so it doesn't include the 7 at all. In some other languages you do 1 to 6, and C you'd have to figure out how to squeeze all the integers into 6 equal sections. But just focus on those 2 things if you're using pseudo-random numbers. Let's look under the hood and see how this works. That's apparently walnuts, but that's squirrels for you. Probably not doing the cartoons, but I digress. So, we've been generating, well, not random numbers, pseudo-random numbers for a long time. So these are actually random. We know definitively what we get each time, and we're missing one in there. Whether you can actually generate a real random number is probably more of a physics question, best done over a pun later on. Basically, I don't know anymore, which is fine. The oldest style of pseudo-random number generators take the starting number, the seed, they can multiply it by something and add something. If you take an x value, multiply it by something and maybe add something, and plot all the values, you get a straight line, so it's called linear just means a straight line. Basically, it's not got something squared in there or any complicated stuff. Just multiplying and adding up. And then the trick is you take that value, modulo some number, and then things seem like they're chopping around a bit. And that gives you the sense of unpredictability. Loads of random numbers tended to be what they call multiplicative, linear, congruential general vectors. The congruential just means it's doing mod, modulus operator on the end, right? And if you pick the right values for the constant a and n, then you can get a nice long series or sequence of random numbers. So if we take one of these, a times our starting number, take it modulo n, sometimes we get loads of different numbers, but eventually, if we get a number we've already had, it'll cycle back round and then we know what's going to happen next. What tends to happen if you take n, the thing you're doing the modulus of, as a prime number, it takes longer to cycle round. But even then, if you do the maths for it with that, which I'm not going to try and do now, because it turns out I can't do mental arithmetic, stand up and talk at the same time, there's too much multitasking. But if you take a as 7, you get the full lot of 11 different numbers. If you do 5 instead, it cycles round more often. And if you're not very careful, if you don't take a prime number, you get things collapsing down. Again, if you work through the mental arithmetic using a is 4 and n is 12, you start with 1, you hit 4, and then if you do the 4 times the 4, take off the 12, you get 4 again. Now we've got 4, and we know what comes after 4, it's a 4, we're stuck with 4 all the time. Is that a random sequence? Well, no, it's not. It's a pseudo-random number. We can work out for the maths exactly what's going to happen. And there's some number theory hiding in here about which numbers you pick, and what works and what doesn't. Which is why it's called a programming language, is choose values for A and N for us. And that's good enough to get some, just set up some card games or a bit of interest in the games you're writing. As time's gone on, we've come out with more and more complicated things. So there's something called a Mersenne Twister, which is hiding in a lot of the Python libraries. It's there in C++. I haven't looked up what's happening in C#. I suspect it might well be a Mersenne Twister. That does something like what we did just now, only a bit more complicated. It doesn't just do multiplying and adding up. It also takes a chunk of bits from the last number and a chunk of bits from the previous number, twists them round and spews out the next number. So it's got more operations going on, so it's a little bit slower. But because it's using some of the last number and some of the number before, when it hits one number, it's already seen. The next one that comes out might be different. It sounds a bit more random. Is it random? No, because we can work out what we're going to get next and we can write tests around these. So, but it's pretty good. I've noticed some things on the internet saying it's not, there's better ones. I don't know what better ones are. Just the linear congruential ones, good enough for setting up some games, and that does me. Little aside, I said we've got linear things, so we weren't doing anything squared. If you do a number squared and take 1 from it, well, if you start with 1 and do 1 squared, you get 1. Take 1 from it, you get 0. And then if I do 0 squared and take 1, you get -1, so that's the left-hand column. You see that flip-flopping between two values. Okay, that's not random at all, that's fine. If you try some other numbers, you also start seeing some flip-flops going on. But if you go outside of the boundaries slightly, then sometimes the number just gets bigger and bigger and bigger. Anyone recognise this x squared minus 1 and know where I'm going? Steve does, because he's already heard. If we move away from just real numbers, and we'll start with 0. We won't argue about what starting point we have. Square where we are and subtract a complex number. If you don't know about complex numbers, we've got 2 parts to them. And if I multiply, the second part's an imaginary number, and it's the square root of -1. That kind of doesn't matter. If they're 2 numbers, then I can start plotting things. And if I colour in black everywhere where it cycles down or collapses, and use a colour for how much bigger things get if it doesn't cycle down or collapse, you might recognise the Mandelbrot set. Now that's about chaos. Now that's just falling out from that x squared minus 1 equation. But trying to work out whether you're going to collapse down or zoom off to infinity is hard. We can do some maths, but the boundaries between it collapsing and getting much, much bigger are really complicated and difficult. And if you get things off by 1 decimal place, you'll move from a stable region to things like feedback loops and complicated stuff happening. The point about chaos is one small little nudge, and then you can definitively work out what's going to happen, and that's therefore not random. Tiniest bit of change in the initial conditions is known as the butterfly effect, which you tend to think of as saying, well, butterfly flaps its wings here, and goodness knows what's going to happen somewhere in the future. Now, goodness does know, and you can do some maths, if you've got exactly the right initial conditions. So you can get chaotic systems, but they're still deterministic. It's just trying to put precisely these starting points into a computer system is surprisingly difficult. Chaos isn't the same as random, and we still don't know what random means, but that's fine. You could start doing other things. You could do 2x squared minus 1, then all kinds of chaos. Well, it's not chaos, it's just surprising stuff, and you have to do some number theory to work out what's happening. And some of the cryptographically secure numbers start doing crazy maths, like squaring things rather than just multiplying and adding up, which makes it much harder to crack and work out what the numbers were. We haven't got time to go into those, and I don't know much about them, only a little bit. So, let's ignore chaos, let's ignore cryptographic random numbers, and just think about using random number generators, these pseudo-random number generators we've thought about. So, smack over the flame. Well, we'll get there in a moment. So, sometimes, we've talked about the seeds, so if I set a starting point, that's my x0, and then I can work out what's coming next. So sometimes, if you want to test your code, you could try using the same seed each time. If you use the same seed in the same language, some of the same, like C++, but do it on different operating systems, you'll have a different library going on, you'll get a different set of numbers. If you've got a set of tests in Python, and you upgrade to a newer version of Python, and you are relying on setting the seed to spew out some numbers for some tests, you might well end up with different outcomes, so you might have to rebase all your tests. So, though the documentation will say, if you use the same seeds, you will get the same numbers out. Just a little caveat about it. It might depend which platform you run it on, and you need to make sure you've got the same version of the language or the library going on. Let's have a little think about some basic games. So rolling a dice, that's somewhere where I might want something random. That's quite straightforward. Spot of Python there. Of course, there are 2 ways to do this. So, 2 questions, right? Is it default seeded in Python? Or do we need to seed it ourselves? Python seeds it for us, so we don't need to. And we need to think about whether I need to go from 1 to 6, 1 to 7. And in Python, of course, we've got 2 ways of doing it, and they're different, so just concentrate and remember which one's which. I said C is a bit more complicated, so in C we need to seed it ourselves, and it's quite common to start time with null, whatever that means. Well, that means now, obviously. Right? If you do that in a tight loop, if you'll set off several simulations, they're quite likely to all end up in the same seed and do exactly the same thing, so that's not necessarily a good idea. I suppose you could try and generate a random number to get a seed, to seed your random. We haven't got time for that. You'll see quite a lot of people, if they're trying to deal with a language like C, if I wanted 1 up to 6 to simulate rolling a die, I'd do modulo 6, right? But the maximum integer isn't a multiple of 6, so I've skewed the buckets I put things in. So it basically can't divvy up all the integers into 6 buckets and have the same number in each bucket. So that messes things up, and you have to start doing a little bit more maths to use this properly. Python will just give me a number between 1 and 6, or 1 and less than 7, depending on which function I called. Rolling 2 dice. Well, rather than just going random, give me a number, you can just create your own generator, whether you need to or not. Probably if you're just writing a little game or coding your way out of a paper bag, you don't need millions of different numbers. Probably be fine, just give me a random int. Pick a card. Well, right. I can choose between 1 and 52 and then map them back to cards. 2 questions. Do I need to default seed it or not again? This is in Python, so no. And I think I've picked the one that gives me 1 up to 52 inclusive, but maybe check it's doing the right thing. Shuffling cards. Random shuffle. If you wanted to do a random shuffle in C, and also had a long discussion with Steve about the best ways to do it in C#, which we might discuss over a beer later on. There are lots of different ways of doing things. If you were doing some computational biology and doing some gene sequencing, I wanted to shuffle bits around then, just bear in mind that if you've got a sequence of more than 2,000 or so, you're going to get in trouble, and you might need something much more powerful than a much longer random sequence. So it's fine for a deck of cards, but if you're doing some serious things, big amounts of data, the basic things might not quite be good enough. You might need to do some background reading. So if you wrote shuffle yourself, how would you shuffle 3 cards, say? Does this work? It's kind of pseudo C-sharpish, I guess you can half parse it if you squint. Musing. I'll go for each card, take the first one, pick another number and swap them. So the first one, 1 of 3, I'll pick 1 of 3 cards, and then for each of those, I'll pick 1 of 3 cards, and then for each of those outcomes, I'll pick 1 of 3 cards, which means there are 27 possible shuffles, right? But I've got 3 cards, there should only be 6 possible permutations, so it looks sensible, but sometimes you need to stop and just do some arithmetic to check you're doing it right. Or use a programming language that implements shuffle for you so you don't get it wrong. Do that. Get someone else to write the code. It's probably buggy as well, but it might be less buggy. There's an officially named algorithm for doing this. You need to make sure you start at the end, and once you've moved the 3rd card, you don't do that again, and then you just get the 6 possible shuffles. Or like I said, just find a library that does the shuffles for you. Choices. So this is one I have to concentrate on as well. If I want to pick 3 things, I could pick a card and put it back in the deck, pick a card, so sampling with replacement, or I can just pick 1, 2, 3 without the replacement. Again, some languages support this natively and some don't, and if you were to try and implement it yourself from scratch in C, it would be a fun afternoon, but you would probably get it wrong several times over. So we're all about replacement on those, just watch out for that and think about what you want. So we're supposed to be on the testing track, so let's have a little think about testing, some simple things. It's really easy, as soon as you've got some random behaviour going on, you start mocking everything out and you end up just checking that you are actually guessing something out of your random number generator. You're supposed to be testing your code, not the library code. So let's check our code, right? So I've said, some people say, if you just use a known seed, then you get the same numbers each time. And we know we need to watch out for if we change the operating system or the library or the language version, that might not happen. Something I found useful sometimes is just completely stub out or mock out the random number generator and just return 0 each time. Particularly if you're doing some mathematical modelling. Because a lot of times you've got a big sum with some random numbers in. If loads of the numbers are 0, you might be able to work out in your head exactly what you want out the other end. I was working on a finance library with someone once, doing some really weird things. So I bolted in a test that just returned 0 instead of a random number. We got one bit of pricing curve like that, and another bit over there, so we've got this big jump between the two things because somebody had put a greater than rather than greater than equal. And then I joined the bits curve up, it was all fine. No random numbers were involved, just sent in a 0. So yeah, try using a 0. You could seed things and say, well, I always get these numbers out with this seed. But you might not have, you're not then thinking about what your code's doing. So think about what you're trying to test. So, yeah, very, very long point there. But again, you can seed your random number generator and record what it does at the moment, but there's so much more you can do to check the code's behaviour. Let's look at a couple of questions from Stack Overflow and the suggested answers and see what we think. Feel free to say something or just sit in a stupor full of cake after lunch and just have a dream. So everyone's got a hit function in some role-playing game, I presume, that calls random int at the beginning to work out what the damage is, I guess that's short form. Question, how would you go about testing? What would you do? The suggested answer, the function was called hit. The suggested answer was to write a test called test player hit missed. Yeah, I would have called it something else. Yeah, that's not, okay, fine. And this asserts that the monster's life is 55. Oh, because it always returns -3. Yeah, okay. At this point, I'd be thinking my hit function would do the hitting, and I might just send in the value, and then I could test that a hit with a negative number reduced the life and a positive number increased it, or something like that. So I would actually reconfigure this.
I hate this. I hate this.
Yeah, I just got fraud with the test player hit missed and then just lost the plot. But if you just got one test there with a value of -3, then my brain's going, what if it's 0? What if it's now? Could it? Well, perhaps we should be spotting those. Before that point, I don't know. Yeah, sometimes calling out to a random number library right in the middle of a function sets you up for convoluted code where you have to patch things from the outside. Just send the number in, check what the hit does with a specific number. Much easier. Another one, right. So, a comment says it all. I'm going to return the indices at the max value of a list. It's like a list, but we've run out of values. It happens. If the maximum value appears more than once, we choose one of its indices randomly. All right, fine. So they've shuffled everything, sorted it, and then found the largest one. You can see how that might give you a different index if you've got two of the same value. Lots and lots of answers, all stack overflow, suggesting answer. Okay, so we stop the shuffling everything, which is kind of fine. So if you can't pass Python, it's just saying whatever you send in, you get back the same thing. So we stop the shuffling, the list stays as it is. Now I've got one test that checks the max index of 4 numbers in order is the last number. Okay, but like, what if the list's empty? The shuffling bit's kind of not pertinent, and at that point, I'd be tempted not to patch out the shuffle. It's fine if it shuffles things around. If you want a function that always returns you the maximum index, then I've had several test cases for that, and I would include some examples where I got some numbers that were the same, given that was the kind of use case. Yeah, it's quite fun looking at other people's answers on Stack Overflow, just having a little think about things. Really? So we've talked through some different alternatives to just those two. But if you've got some code with some random numbers in, go back and look at your test to see if it's actually testing your code or not. That's very important. Yeah, okay. Just a little summary there. So we've talked about how to test things and properties. Well, there's another thing you can do with random numbers. If you're expecting on average to get half heads and half tails, it might be worth checking that actually happens. Just in case you seeded things wrong or messed up C's random and done something bad there, so it's worth doing that. You can use randomness to do other things as well and test your code in other ways. Anyone come across fuzzing before? Right, so you just get a fuzzing system to make up loads and loads of random. We still don't know what random means, and I don't think we're going to find out. I'm very sorry. The fuzzing will then try and flush out some edge cases, and it might actually try and crash your code and things, because it will try all kinds of different inputs, including names or whatever. And then that's a really good way of flushing out things. And maybe a subset of that fuzz testing is property-based testing. I talked about saying expecting half heads and half tails. And also the maths example I had earlier, curve didn't join up, just saying, I expect there not to be any discontinuities, and then it could have found it, and it would have found a less than rather than less than for me. So randomness, even though we don't know what it is really, really useful and quite good fun. Or just simple things. If you've got a CI server running some tests, maybe your testing framework allows you to run things in random order, and that will find a surprising way, probably of bugs in your tests rather than your code, because sometimes you've got a state going on and do it, try it out. So at the moment, so far we've looked at some examples with rolling dice and picking a card. Those are all equally likely with uniform outcomes. But there are other types of random number sequences, particularly things involving floating point numbers. If you look at people's heights, you tend to get a lot of people around the average height and fewer really tall people and fewer really short people. So loads of other distributions. And you can build all of the other distributions from a basic C's random integer. You have to know some maths and some probability to work that out. But again, loads of programming languages have that coded up for you. It's quite fun to try and roll your own, and then work out how to test it. But a uniform whole numbers, you expect, for example, if I'm rolling a dice, if I do it 120 times, I would expect about 20 each. If it always came out with precisely 20 of each possible number every single time, we might start suspecting that the random number generator was completely random. It could happen. it might just be close. And on average, if you do enough, you'd expect it to kind of average out. Like I said, with heights, you tend to get more in the middle and fewer off on the edge. But that's the Gaussian or bell curve. And there are loads of distributions, and there's no time to be listing all of them. There's no time anyway. They're all useful for different things. And again, like I said, you could go from just uniform integers and do some maths on them to get this bell curve out. But again, most of the programming languages have got libraries that do that for you. So, more importantly, we said why. Do we care? We don't know what. We know there's no such thing as a random number. We're not quite sure what a random sequence of numbers is, but we've seen how to generate a random sequence of numbers. Why do we care? Because it will make my race out of my paper bag slightly more exciting. We're not going to do exactly green blobs all doing one step at a time. Let's have some doing one step at a time, some picking uniform random integer, and some deciding pulling a number from a normal distribution. Set these up so the stepper ones that do the same each time always move 20. It might be pixels, but I've scaled it, so it probably isn't. I can't remember. It doesn't matter. It's a number. And the average for the other two distributions is the same. Who's going to win? So, green ones, lockstep, same size each time. Uniform integers next, and then the normal distribution. Potential. Oh, it is more interesting than just the that's what we've got. Oh. Sometimes the normal ones go backwards. Oh. But they all escape the paper bag, and no blobs were harmed. Yeah, it's nice and simple, but it's more interesting. And it's not actually doing anything random. We could work out what would happen if we knew the seeds, but that doesn't matter. It's nice. Why not? And so you could even write your own random numbers. We've seen things with stuff squared a little bit, cubed. We can do other operations. Are they actually random? There's a whole battery of tests which started with something called Die Hard. I guess it's a joke on simulating Dyson being quite hard, and Bruce Willis, and now there's a Die Harder, and then there's whole suites of tests. You go, is this really random or not? No, it doesn't have enough things that have got the digit 1 repeated often enough, or it's got too many ones, or... I don't think that makes something actually random. That's just what we want to be happening in order to use these, in order to write some games engines or do math simulations and so on. And it's really fascinating looking through how we test these for randomness. And we go, no, there needs to be an equal distribution of ones everywhere. So we're saying it mustn't be random at all. It must have all these really precise properties. But that's still cool. It's erased my way out of paper back. That's great. If you start looking at things that go wrong with random numbers, including the cryptographically secure ones, then that's like a fascinating thing to look at. If you're doing cybersecurity, then that link's worth a look. So, just on the side, I programmed my way out of the paper bag in a variety of different ways. Like I did previously. The source code's up on the PragProg website, so you can feel free to snaffle that and find loads of bugs in it and make it better. Code your way out of the paper bag, tell me how you've done it, and I'll send you a certificate. Also, by trying to learn how random numbers work, I got bored and distracted myself. I started writing a book about C++ to remind myself how C++ works. There are 3 chapters up on the Manning's Early Access program at the moment. And I've said I can give away 3 free books. I'm from Kent, I can't hear the difference between 3 and free, but I'm sure they sound different. There are 3 cards on chairs randomly placed, or placed by Maya, possibly not randomly. If you'd like a copy of the book, scribble some contact details on the card, give it to me, and I'll get them to send you a free ebook. Basically, I don't know what random really means. I know chaos is absolutely fascinating. And writing some games for your computer's fun.
That's it.
Thank you.